good. Yeah, so now we will talk about the amperometric sensor. So what is happening here? An amperometric sensor that measures the current that is generated by an electrochemical reaction at a fixed voltage. So there we are measuring the voltage in the potentiometric sensor. The voltage was changing, right? Time after some time interval. But here the voltage will be fixed. So we will measure only current. So how these amperometric sensors work? A constant potential here is applied between a working electrode and a reference electrode. So the analyte, that can be glucose, oxygen, those undergoes an oxidation or reduction reaction at the electrode surface, and this reduction reaction actually generates the electrochemical current. That current we are going to measure. And the magnitude of the current is directly proportional to the analyte concentration, either positively or negatively. So there are different kinds of amperometric sensors. Can be single potential amperometry, chronoamperometry, pulsed amperometric detection. So the single potential amperometry, that means it measures the current at a fixed voltage, the most common one. There is also pulsed amperometric detection. That means it uses the voltage pulses to detect complex molecules like carbohydrate. And the chronoamperometry, we also use it sometime. It measures the current over time after applying a potential step at a fixed potential actually. You just need to fix the potential and the time, and it will measure the chronoamperometry. That means it will measure the current. And there is also multi-step amperometry, so it switches between different potentials to detect multiple analyses. So here you can see one sensor that has three electrodes, counter electrode, working electrode, reference electrode. Yeah, so we can measure this kind of in the, and that sensor is always connected to a potentiostat. And in the amperometry sensor, we can use this kind of sensors. So let's go to another example. So this paper is talking about detecting what nitrates biosensor, right? Amperometric nitrate biosensor based on carbon nanotube, polypyrrole, and nitrate reductase biofilm electrode. So from this title, you can see that in the sensor surface, there will be the base thing at first, maybe silver or carbon. And on top of that, there will be carbon nanotube. And on top of carbon nanotube, there will be polypyrrole. And then there is the nitrate reductase, that is the enzyme they are using. So we can call it biosensor. So they are using the enzyme nitrate reductase, which will capture the nitrate, right? So there will be a reaction with nitrate. That's why we are using nitrate reductase enzyme. So it will be very specific to detect nitrate. So here you can see the construction and characterization of an amperometric nitrate biosensor based on the polypyrrole carbon nanotube film. Nitrate reductase was both entrapped into the growing polypyrrole film and chemically immobilized. So what is happening here? The optimum amperometric response for this nitrate was obtained, and they said 0.1 molar phosphate buffer solution you have to use for this solution, and the pH must be 7.5, and also they use 7 millimole of potassium ferrocyanide. So the concentration when you are going to prepare different kind of nitrate solution, that concentration they are preparing using PBS, potassium ferrocyanide, and making the pH 7.5, okay, to get perfectly the curve for nitrate. I mean, get the current curve. So here the reduction of nitrate reductase to its native form is actually conducted by electron capture of the oxidized nitrate reductase enzyme. So what is happening here? You can see this when there is a electron is coming from the electrode. That with the help of the electron, this is the ferricyanide that we are using in the solution. The ferricyanide is going to reduce to reduce to ferrocyanide, and the ferrocyanide, when it is ferrocyanide, oh sorry, that is the ferricyanide. So the ferricyanide is yeah, so it is going to reduce to ferrocyanide. At the same time, this oxidation has been happening. So the nitrate reductase, which is in the oxidation form, is going to reduce to nitrate reductase, reduced form. And when there is the reduction form, it is going to oxidize again. And when this nitrate reductase is going to oxidize, going to this its oxidized form, the nitrate is going to be reduced, and with the help of this nitrate reductase enzyme, and nitrate becomes nitrite. So this is the electron transfer mechanism of this nitrate sensor using this nitrate reductase enzyme. So in this figure, you see this figure that illustrates the typical amperometric response, that current versus time recording after the addition of successive addition of the same amount of nitrate solution. Initial nitrate addition started at 0.25 millimole, and then constantly they are increasing the same amount of solution over time, and we're getting higher current, right? So the response time of the biosensor for nitrate addition was observed to be 20 seconds each, and yeah, the nitrate calibration curve here. So we're getting the current, and the current versus different nitrate concentration. We're getting the calibration curve, and the calibration curve is really good. The nitrate calibration curve was yeah, here. The nitrate calibration curve obtained from current time recording in linear range of 0.45, starting from 0.45 millimole nitrate to 1.45 millimole of nitrate. So that is the detection range of this sensor. It can detect between 0.45 to 1.45 millimole of nitrate. Okay, we can discuss another amperometric sensor, that is the enzyme-free amperometric sensing of glucose using copper oxide nanowire composite. So they are using two different thing. One is copper and another is copper oxide. There is a mixture of copper oxide nanowire, and they are detecting glucose, and they are saying they don't need to use enzyme free. Okay, so how they are doing it, we can see here. So the modified electrode efficiently catalyze the oxidation of a glucose at less positive potential. So it requires very less potential, that is 0.30 volt. We're not talking, we don't need actually the volt, we just need the current, right? So here the electrocatalytic activity of this Nafion copper oxide nanowire and GCE, that is the glassy carbon electrode. So there are different kind of electrode. At first I showed you the screen printing process of different kind of electrode, but this is the commercial one, that is called glassy carbon electrode. You can easily buy it, and then you can modify the working area of that one. So they are using copper oxide nanowires, and on top of it, they are also using Nafion. Okay, so this what I'm telling is the electrocatalytic if activity of this Nafion copper oxide nanowire and the graphene oxide electrode towards the oxidation of glucose in an alkaline solution. They are doing it, right? So in this figure, you can see it displays the CV. There is a cyclic voltammetry of 2 millimole of glucose, right? Yeah, 2 millimole of glucose in 0.10 mole of sodium hydroxide solution at the Nafion. Two different kind of electrode they prepare here. One is Nafion copper oxide nanowire GCE. Another one is Nafion just copper oxide without using the copper oxide nanowire. Okay, and from the figure you can see here that it is showing higher uh, current for the one which you are using copper wire nanowire. So the sensitivity they are getting high when they are using the copper nanowire. So I think for the rest of the experiment they use the only the copper wire nanowire with Nafion on top of the GCE. Okay, so in this present this in this experiment on the performance of the sensor, which one is higher, I told you already. So this amperometric current versus time curve for detecting this glucose at the Nafion copper oxide, yeah, glucose was injected into the stirred 0.10 mole of the solution at regular interval. You can see that they're injecting the glucose. So at first it was 0.1 millimole, then 0.2 millimole, then 1 mole, 2 mole, 3 mole. They're just increasing constantly. And the current is also increasing over time. So, and then they're getting the calibration curve using the different glucose concentration in millimole versus the current in microampere. So the amperometric response for this present sensor at higher concentration was tested, right? And you can see the glucose concentration there starting from here is like 0.1 or something till 12 micromole. That is, the detection range is really good.